Johnston, who is going to hopefully blow your minds with unlocking APIs using GraphQL. So take it away, Dylan. Cheers.
Hello? Yep, sweet. Sorry, I've lost my mouse. It's on that screen. Where does that one relate to this one? Yeah, there we go. It's off to the right. Hello. My name's Dylan. And I work at Coria, formerly known as Family Zone, as a software engineer, and I'm on the core platform team. And so we primarily build backends for other backends and other crimes that we're forced to commit by microservice architecture. I want to talk to you today about our experience with adopting GraphQL, why we felt it was a good idea in the first place. Hello? Oh, back. How it went and what we learned from that experience. So we'll start by talking about everyone's favorite API style, which is REST, and why it lies to you. And every good talk starts with an inflammatory statement that you then walk back with caveats. As programmers, we love taxonomies and grouping things together into nice, beautiful, loosely coupled abstractions with clear separation of responsibilities. And so when faced with needing to build a new product or app, we have a classic front-end client probably written in React or maybe Svelte if you've got too much PTSD from React. And then some backend that presents a beautiful REST interface where your entities are neatly grouped into resources with all of your favorite HTTP verbs like post, put, get, delete. And you can go to bed and sleep soundly at night knowing that all of your I's are dotted. You do dot I's, yeah. All of your I's are dotted and all your T's are crossed. And this works great if you have what I like to call BFFs, which is backend for front-end services, which is to say that your backend exists just to be the backend for a single front-end client. Because even like the simplest website is technically a distributed system these days. So, but before you get too comfortable with being well-rested, a calendar invite appears in your inbox. And it's from another team that wants to start consuming data from your service. Because like good microservice designers we are, you own the hero service. Oh, sorry, actually, I should have talked about what the API is first. GraphQL documentation uses Star Wars as its kind of data model for all of its examples. So if you go to the GraphQL website, it's all like, who are the heroes, who are their friends, and stuff like that. So I'm using that for this example as well. And so, yeah, you own the hero service. And so if anyone wants to know anything about the heroes in Star Wars, they've got to come to your service and ask about it. Because it's still the 80s where hard drives are the most expensive piece of your hardware. And so we can't denormalize our data. Like, you own heroes, and everyone has to come to you to get the heroes. This other team is building some kind of dashboard. And they need to not just display the individual heroes, but they also need to include the friends of those heroes so that we can kind of like see all at once, all the heroes and who their friends are. And they can't really make multiple round trips to your database, to get the heroes and then each of those friends. Multiple round trips to your backend. Because it's a latency sensitive thing, and this project's already behind schedule, and can you please just add this? Begrudgingly you add a query parameter to your API, so like include friends equals true, you can still sleep alright, but there's kind of like a P, like the princess with the P and the mattresses that's kind of like keeping you up at night because you've got this little like quirk now in your API, and then another calendar invite appears in your inbox from yet another team that wants to start getting data about heroes. But in this case, your default data that you return about heroes also includes a rather expensive to compute field, which is like the starships that those heroes pilot. And this is a really latency sensitive application. So we don't want to pay the cost of computing that data. So can you please just add another query parameter to your API to exclude that data? And also this project's also behind and now you're blocking us. This slightly dramatized story is kind of what was happening to us. Like we had this beautiful API that we built for other consumers of our services that our teams owned. And then as adoption grew of that service, the number of query parameters in our API was just multiplying out of control because every team needed slightly different representations of the data. And so very quickly, our loosely coupled backend doesn't look so loosely coupled because REST forces these kind of like resource paths where it's like, here's where you come to get heroes. Everything that cares about that data gets funneled through that single route. And then you kind of have to then branch back out using these query parameters. And so your REST API kind of needs to know about every single consumer because you own that data and you present it to the consumers. And so you need to make sure that you have efficient representations of that data for each of those consumers. And so this is what I mean when REST APIs are kind of full of lies. They don't actually achieve proper service decoupling. So there's a few problems in this dramatized, based on a true story example. And the first is what you might be familiar with as the n+1 query problem. And so what we saw is we have some data, heroes, and they are related to some other piece of data, they're friends. And so when we want to fetch that data, we first fetch the root, and then we have to make n follow-up requests to fetch each of their children, each of the related pieces of data. The other problem we had is overfetching and underfetching. So once again, because all of these different clients all go through the same path, we must return the superset of all of the data that they need. Or where it's performance critical, we start adding query parameters in order to toggle certain fields on and off so that other people consuming the API don't need to pay that cost. And then the last problem we had is, server-client coupling. The server really needs to know about every single way it's going to be consumed in order to be able to provide efficient access to that data. There's this really great documentary on YouTube, which you can find at this QR code. I promise it actually links to the real one. I'm not doing the Rickroll from last year's latency with the QR code. And it talks about the invention of GraphQL at Facebook. And as much as we like to think of ourselves as special, there are very few companies that face truly novel engineering challenges. And so GraphQL was born at Facebook in 2012 as they were transitioning to mobile. And so up until that point, their mobile app was a very thin wrapper around their website, and the website was server-side rendered, written in everybody's favorite language, PHP. And so as they were trying to build out a native mobile experience as mobile was really exploding, I think it's easy to forget that not everyone had a smartphone just 10 years ago. It kind of feels like they've been around forever. Their APIs were not set up to move all of that complex data fetching to the client, because the backend was responsible for populating the timeline with all of these different heterogeneous data sources with complex relationships. And so they were faced very much with this problem of how do we efficiently express the need of the client to get the data that it wants. And so what they invented was essentially a DSL, or a domain-specific language, for expressing all of the problems I was talking about. And so if you kind of squint here, the top is the GraphQL, and then the bottom is the response object. If you kind of squint, it basically just looks like JSON with just the keys and not the values, and I guess no quotes. But there is a kind of pretty strong correspondence between the input query structure and then the output data that you can see there. And so you can specify exactly what fields you need, and so that solves the overfetching and underfetching problem. You only fetch the data, or you only pay for the data that you actually care about. The second, which is a little bit too small on this projector, is the ability to express hierarchical relationships. So I said before that heroes have friends, but those friends are also heroes, and they have friends. And so we can nest several layers deep here. So you can see we've got the top hero, which defaults to R2-D2. Maybe that's a controversial opinion, that he's the real hero of the Star Wars series. And then his friends are Luke Skywalker, Han Solo, and Leia. And then we go one layer further to get their friends, and we can see that nesting for. So it really presents an easy way to compose hierarchical data relationships. And just as a comparison to how that might look in REST, you typically have your sort of normalized resource path with some ID, and then you can express data relationships by kind of using sub-resources. So we might say, give me the friends of that hero, and then give me the spaceships of that hero. But critically, if you wanted to get both of those, you can't do them in one request. You have to make at least 2 separate requests, because those are separate relationships, and you can't really express that in a single path, right? So part of REST problem is the fact that it needs to be serializable down to a single path, if that makes sense. So it becomes impossible to express side-by-side relationships. And then typically you may have, when you get the resource without the ID, it gives you all of them. And then the question is, what happens when the hero type appears elsewhere in your API? So as a sub-resource of some other resource, do you then take all of your friends and spaceships and then make them available as sub-resources of that sub-resource? So there's a composition problem here, whereas in GraphQL, if we just go back to this, oh no, actually it's better. Yeah, better here. wherever the resource appears in your graph, wherever the type appears in your graph, all of the fields are going to be available there for you to fetch, right? So the data relationships compose much better and automatically for you based on the graph rather than having this awkward situation where you need to sort of come up with that for your REST APIs. But I did skip past talking about versionless schema. So the other major value proposition of GraphQL is that it has a versionless schema, and apologies, this GIF kind of like flies by a little bit too fast. I should have tried to slow down the frame rate of it. But we start by modeling this film as having a director represented by a string, but then we realize that we care about more than just the name of the director. So we add a new field, which kind of like points to a richer structure where we can have more metadata. And then we're able to mark the old field as deprecated, and then anyone consuming that will be notified that field is deprecated, and then to access that via the richer object. So that allows us to evolve over time as we evolve our requirements and understandings, which is pretty cool. Yeah, and the other thing is that the schema is extremely strongly typed. It explicitly models nullability. They encourage to use, so everything is nullable by default, which is maybe a little bit controversial, but when we talk about schema stitching, there are network failure potentials all over fetching your data, and so it's a really good idea for your clients to really embrace what do I do when this data isn't available, so that way you can have like graceful failover. So that's the reason why it's nullable by default, but you can just put an exclamation mark on any of these to declare them as always being present. And then what that strongly typed schema allows us to do is really world-class developer tooling. So you can see here, this is the classic graphical playground, which comes with most server implementations of GraphQL. So we have autocomplete and like sort of warnings about fields that don't exist, which is really cool and allows developers and even sort of like more non-technical people to prototype queries and sort of interact with your data. So we provide, the service I work on is entirely internal, and so we are able to provide this playground in all of our environments, including production. So it's really easy for people to go in and quickly have a look at sections of our data, which is really cool. And so I'm sure, being at a tech conference, you've all seen the innovation adoption lifecycle before. People fall into one of these buckets, sort of innovators, early adopters, early majority, late majority, and laggards. But this occurs not just at the level of the entire industry, but it's kind of like a fractal where it occurs just within your company, and then also even within teams. Individuals within teams fall into these adoption life cycles. And so it would be completely infeasible for me at a company of Coria's size to go around to every developer and pitch them on GraphQL, right? So it is key when driving an adoption of a new technology to identify which teams within your organization fall into this adoption curve and start with the innovators. Because what we want is something like this, like invasion of the GraphQL advocates. Like we want to make it to go viral. Not a lot of fan of classic sci-fi horror in the audience today, because if we're able to make it go viral, then it sort of like scales much more easily because we're able to turn other people into advocates for GraphQL. This dark scheme does not work very well in this lighting, but the key thing in our experience with driving adoption of GraphQL was that developers don't really care about all that other stuff I've talked about. The thing that they care about is making their job easier. And the thing that was always the switching point whenever I was pitching it to people was code generation. So I mentioned before that the schema is strongly typed, and the GraphQL community has really embraced this notion of code gen, both for the server and for the client. And so if you have a strongly typed server implementation, and then the schema is strongly typed, and then the client is strongly typed, and you're using code gen, you can basically rule out null pointer exceptions from your entire stack. And it also just makes interacting with the API so much easier because you just go in, change your query, rerun the code gen, and now you've got all your types in your language and it's all good. And that was the key moment when trying to drive adoption of GraphQL at Coria for most developers that I interacted with, was once they saw the power of code gen, they're like, yeah, okay, this is awesome. This makes my job so much easier. And so this is what we want. Yeah, scene from Invasion of the Body Snatchers did not land the way I wanted it to. If you like The Thing, like the original 80s one, I'd highly recommend that movie. It has a very similar kind of vibe to it. And so that's all and great, but like, how do we actually build this thing? GraphQL says very little about how to actually build these things. It's a very unopinionated spec. And there are lots of difficult engineering decisions that you have to make. So GitLab has an excellent GraphQL style guide. Highly recommend checking it out and then following it, because they have a lot of experience with building out their GraphQL API. And so we had, and then the other spec is Relay, which is from Facebook, and that is primarily concerned with pagination. And so we were following Relay from day one because I've had experiences with bad GraphQL pagination in the past. But we unfortunately didn't adopt the broader style guide of GitLab until much later, and so we did have to do some reworking. So yeah, if you're going to build a new API, please check out the GitLab style guide in GraphQL, because it makes all of those choices for you and also explains why those choices are important. But in terms of actual code, so hopefully most people here are familiar with JavaScript. It's incredibly easy to implement a GraphQL server. So we have our sort of like small schema on the left here. So we have the entry point into GraphQL is this top level type that always exists, which is called query, and then we define fields on query. So there's this hero, and then the hero takes an episode and returns a character, and then the character has these fields. And then to do the implementation on the right here, we just define this object called resolvers, and then for each type in our schema, we can define fields on that type, which essentially resolve data for it. So in this example, we have the top level hero query, which takes an episode and then resolves into that character object. But critically, the friends object on the character is its own resolver. And so it can go off and fetch that data from somewhere else. And so this allows us to compose in, so these would be your, like your REST endpoints, typically. So you'd have, like your hero and then getting the friends. And so here we basically just turn those into resolvers and then let the GraphQL server compose all of those endpoints together for us. So it's not quite a one-to-one transformation like I've kind of made it out to be, but you basically just take all of your normalized kind of REST resources and then stick them into a graph and then just let the server compose them for you. And that's kind of the key to GraphQL is it doesn't actually solve n+1 and all those other things. It just moves those problems to the server where they're actually easier to solve. So a client can always compose your REST endpoints together, but that's multiple round trips between your client and the server, whereas here we're doing multiple round trips between the server and the database instead. And so I mentioned just before that GraphQL doesn't actually solve n+1, it just moves it to the server. And so we need another solution to that, and that solution is data loaders. So data loaders are a layer that sits in between your API and your database layer, and basically it presents to the API layer, load me this single thing, and then to the database layer, it presents batching. And so it's responsible for batching stuff together. And so I was wondering what kind of visual could I use to explain data loaders. And so this is a real trace from our monitoring system. And to just kind of try and explain it, so over on the right here, you see these multiple green lines. So each of these green lines represents some kind of operation that we're sort of measuring the execution of. And then the orange ones are the actual database executions. And so we've got these 4 lines here and then only one orange line here. And that is the data loader essentially batching all of those resolvers into a single execution. And to show you how crazy it can get, no expectation of being able to read this slide, but look at how many calls are getting batched together here, right? So this is maybe like 50 or so groups that are all resolving these like member counts, and it's all getting turned into a single database call here. And you, unfortunately, Go is not as smart as Node.js. So I believe somebody is talking about the event loop later. Yeah, Aiden, that's right. Node.js can be really smart, and it can just wait for one tick of the event loop and then batch everything off. Go doesn't have an event loop, and so it just has to wait for some amount of time. So you see this gap here? That is the batching window, where it's like any calls to that loader get batched within that window. And so unfortunately, right here, all those dispatches occur in less than a millisecond, but we're still waiting for 5 milliseconds. So tuning that batching window is really important. And I think we can see from this data that we actually need to bring our batching window down quite a lot because our server is a bit faster than we expected. And it's adding about 10 milliseconds latency to this request, like waiting around to like batch things. Yeah, you can see the same thing there. So earlier I made pagination seem a little bit easier than it really is. Because before we had it just as an array, right? So we're like, here's this hero, give me all their friends. That works if the number of friends is small. That doesn't work if you have tens of thousands of friends, right? Like, as some people claim to on Facebook. But at least for us at Korea, we have teachers that are members of just like tens of thousands of groups and stuff like that. Like there'll be some administrator and then they want to be a member of every single group. And so if we ask for their groups, we can't give the client back 10,000 groups. And so pagination is super important for each of those. And so choosing your page size then actually matters an awful lot. So this is, I don't know have enough time to explain how our group structure works. Basically, groups can be related to other groups as a subgroup. And this is a graph of how many subgroups each of the groups have. So we have 50,000 groups here that only have one subgroup. And then you can see this huge tail here. Where like, even off the end here, it's 65,000. Like there's a group in our system that has 65,000 subgroups, right? And so when deciding how, and this is the same data just on a log plot. And so when deciding pagination, cumulative distribution functions are super important. So the way to read this graph is basically being like, if we want 99% of requests, so this vertical axis here is percentage. If we want our P99 request to service all of the data, because like we don't want to be making clients make multiple round trips to fetch all the pages of the data, we need to size it. So if we draw a vertical, I wish I had a laser pointer. Imagine in your mind's eye drawing a line over there, and then where it intersects that blue line, then draw straight down, and that tells you how many we have. And so the P99 for this graph is actually just under 300. And what that means is, when fetching all of the subgroups for a group, 99% of the time, if you ask for 300 of them, you'll get all of them. But then for that one group that has 65,000 subgroups, you're gonna have to make tons of trips. And so if you've got SLOs for your service that you need to respond in a certain amount of time, then sizing your pagination size is really important. And so understanding the cardinality of the relationships between objects in your data graph becomes super important, because if you choose a size that's too small, your clients are now going to be making multiple round trips to you, and like you don't want that. But you also don't want it to be too big that your server gets crushed trying to service this response by giving it back tons of data. Nested pagination, this is a problem we've run into. I've tried Googling this. I can't find anyone talking about this. As far as I'm concerned, there is no solution to this problem. Come up to me afterwards if you have a solution to this problem, if you think you do. But I'm running low on time, so I'm just going to skip over talking the nuances of that. Query complexity. So obviously, you're giving your clients a huge amount of freedom. We're quite lucky that our API is internal, so we don't have to worry about malicious clients. If you imagine something like this, so just 2 levels deep, we're already returning 10,000 results. 3 levels deep, we're returning 1 million results? Yeah, 6 zeros. Yeah, 1 million results. And then 4 levels deep, we're returning 100 million results, right? So you can limit 2 ways, both on you can limit the nesting depth, and then you can also limit the overall complexity by assigning sort of an estimated complexity to each field. And you want that complexity to be strongly correlated with the load that query places on your server. We're not doing a very good job with that right now. Some queries that are actually quite cheap to compute end up with high complexity scores, but it's something that needs to get tuned. Man, really running low on time. Okay, quick demo. I had this up. I was in the other tab of that one. There's my mouse. Yeah, so observability is super key, and oh god. Wi-Fi hotspot? Yeah. Yeah, sweet. So we use OpenTelemetry to heavily instrument all of our resolvers. And so you can see here, we've got all these queries that the clients are executing. We only sample 1 in every 100 requests because like Datadog is quite expensive for this kind of stuff, but I think all of them quite are. So you can see each of the individual queries that our clients are sending to us, like P99 latencies, error rates, things like that. And then we can click in here and see sort of details on exactly like where it's spending its time. You saw those kind of images before. I was hoping to spend a lot more time talking about observability because it's super interesting and super important, but please come up to me and talk to me later about it because I have 30 seconds left. And I don't get to talk about federation, but luckily the guy before me talked about federation a little bit, so yep, come and talk to me about federation as well. Skip. So when should you use GraphQL? if you have lots of clients, if you find your query parameters are multiplying out of control, and if you think code generation is a cool idea, which it is. Arguments against requires rework. It's not quite a one-to-one translation. You can reuse a lot of your existing database access methods and stuff like that, or REST APIs, but it's not a one-to-one. It is additional complexity, and you have to retrain people. And it's not really needed if you have a BFFF service. But in my opinion, I'm running out of time, code generation kind of makes everything else I've talked about not matter because it's such a good thing, in my opinion. And so even if you're not using GraphQL, if you're using OpenAPI, I think that supports code gen. So yeah, more code gen, please. All right, thanks for coming to my talk. The slides are written in MARP, so you can find the source code at these links. And thank you very much.